when a couple is indicated that he is on his station.
Okay, we'll wait.
Yeah.
Thank you.
Yes, thank you.
Yes, we are okay.
So a couple,
Hey,
you will let us
yes,
know when
Jolene, I think we can start.
station. Yes, but
sorry for the.
you need to record. Are you able to record? So we said maybe we wait till you go to your station so that you'll be able to record. Are you able to turn into live on YouTube?
Yes, Jolene.
Yes.
Hello?
Yeah, I was saying maybe are you able to record there, or you have to record from your computer?
On that Sunday morning, when I was on leave, starting to prepare myself, because 3 months they were very bright office same salon that coming.
David, can you also allow me to be able to post on chat to the participants? Because yesterday I could not at all.
Yeah, he has to make you a co-host. You assign also Dr. Cleo and the kids to be co-hosts.
Hello, Stephen and Peace. Sorry, we had some technical issues. So we're the other side trying to resolve with the IT team.
It's okay. We'll wait for you to give us a green light. So go ahead. Thank you.
I think we can now go ahead. Everything is now set.
But I think you need to be a co-host, a couple, and also allow Peace and Dr. Opio to be co-hosts so that they can communicate to the participants directly.
Yes, I am now host. I'm going to make them co-hosts right away.
Oh, great. Yeah, so I think now we can start.
Yes, we can start.
Yeah, thank you.
Okay, thank you everyone for coming, and good afternoon, good evening, and good morning where you are. So we're going to continue from where we left yesterday. So Peace can start from there. Thank you.
Thank you, Stephen. Thank you, David. Thank you, Dr. Para. Good afternoon, good morning, good evening from wherever you're joining us from. We are going to start from where we stopped yesterday. And before we start, please make sure that you have access to the Google Drive. We have uploaded a few things there that we are going to use today, and also some data sets that we are going to use today, much later during the session. So I'll start by showing you what you need to download from the Google Drive in preparation for the session. So we'll continue from where we stopped yesterday. but there are things you have to download that have been put there today that we will need to use. So I will share my screen now. And right now, I am projecting the Google Drive. The Google Drive that contains the data science materials is what I'm projecting. So inside the Google Drive, today we have quite a number of things that have been loaded there that we are going to need. One are R scripts, and two is a data set. The R scripts that you're going to use are here. We have the performance regression. There's an R script. Please download this one from the Google Drive. We have the linear and logistic regression R script. Download this one as well. And then we also have the data science code _1. Yesterday we used data science code R. Today we have a new one. It has more code for us to use today. So this is the third file that you're going to download. The last file that you're going to download is the CSV file for animal data. So once again, you are downloading 4 things from the Google Drive and you're putting them into your folder on your desktop. And you are downloading the animal data.csv. It is a CSV file. You are downloading data science code _1. It's different from the one that was loaded yesterday. So this one was loaded today. And then you also download the performance regression script and the linear logistic regression script. Those are the 4 things that I would like you to download as we prepare to start. And so I will give you 2 minutes to successfully download these files from the Google Drive and place them in your folder so you can be able to access them. Meanwhile, when you put things in your folder, you could as well just open R from within your folder. So that when you open R, you are in the working directory. All right, so somebody's saying, please repeat. Somebody's saying they have not seen the regression. If you're looking at my screen, this is the file that I would like you to download. The first one is performance _regression. The second one is linear logistic regression. Okay, these 2. And then when you scroll down here, we have data science code _1, which is also an R script. And then we have animal data.csv. If you are not seeing this material, then you need to refresh your Google Drive. So you can be able to access the information or the files that were loaded or uploaded today. So we have 1 more minute to access and download and put them in your folder. And then you can confirm if you're done in the chat as we wait. Confirm if you have been able to get all the 4 files that we've talked about. Make sure that you put them in your folder so that it's easy for us or for you to access them when you need them. Okay, somebody has their hand up. You can just type.
Let them type in Q&A. because the general chat is going very fast.
If you have a challenge, you can type in Q&A. But if you succeeded, you can use the chat so we can see. Somebody says we share the files in the chat. The files are on the Google Drive, so maybe the Google Drive link is there on the chat, so you can be able to access the link and download the files. All right, if you're asking about which files we are downloading, then we are downloading performance regression. This is the first one. If you can see my screen, we are also downloading the linear logistic regression. And then when you scroll down, we are also downloading the animal data CSV file. And we are also downloading data science code _1, which is also an R script that is going to help us to continue from where we stopped yesterday. Okay, so you can, if you're done, just confirm in the chat. It's important that we have all the files together, and then we all proceed together. Okay, so it looks like we have successfully downloaded the 4 files that have been specified. Put them in your folder. Put them in your folder. And then we start. So I'm going to R itself. And then we will go to the presentation.
Is the webinar being recorded? Is the webinar being recorded?
Yeah, Stephen, yes, it's recorded. It's already live on YouTube.
Thank you.
Okay.
All right, we can proceed. So when we go to R, this is where I want you to come. So in your R script, we are going to open this in R, and then we go back to the PowerPoint and we guide ourselves on where we are headed to and what we are doing today. So today you will open your data science code _1 that you have put in. It has codes that are similar to the data science code, but when you scroll down, you realize that we added some other codes in here. So make sure that you have opened it and you can see it up here. Make sure that you have opened it and you can see it up here. That's the first that we are going to use for quite some time. And then later we shall use the linear logistic regression. So I might as well close the linear logistic regression so that it doesn't confuse us. So just make sure that you have loaded your data science code _1.r. This is the script that we are going to use. It has information that is going to help us to perform statistical tests, also continue with our visualization. Let me know if you have opened your data science code, but also make sure that up here you are in your data science project. Okay, so the name of the R project should really be data _science, and the name of the script that we are using is data science code _1. So I will pause. You can confirm if you have managed to open that too. If you have managed to successfully open the code. Okay, confirm in the chat. All right, so if they're telling you there's a package that's required and not installed, install it. Install it. If it prompts you to install, install it. I mean, when you reach somewhere down, we will install the packages, but if it prompts you at this point, just click on install. Click on install, make your work easy. File is open, but not in the environment. My environment has very many files from yesterday. That should not be a problem for you. We are going to import the data. My interest is for you to have your code open and running. Somebody says, I have the top isn't reading data science. It's not reading data science because you did not open your project. If you opened your project, I think the person who doesn't have data science here, if you didn't open a project, then you will not have it. But if you have a project, you can just go on your folder on your desktop, like mine here, data_science, double click, and this one here, there's a project here where you see our studio project file, this one. When you click on it and open it, it will open the project data_science. Then you will be able to see it. So double click on this one here so that you're in the working directory that has all this information. The challenge with opening RStudio outside your project is that every time you are importing, it will give you an error that says the file path cannot be found. File path does not exist. And the reason why it gives you that is because the project is not created. So the project that you created on day one is the project that you should be using. If you don't have a project, please create it, and then we can proceed. Otherwise, you're going to have to import data from this environment here so that you can quickly determine where yours is. Okay, so we are now proceeding. We are now proceeding with our session for today. So yesterday, and now I am projecting the PowerPoint. Okay, so yesterday we introduced ourselves to ggplot2. ggplot2 is a package that helps us to visualize information, to visualize our data and relationships in R. And ggplot is very important because it has some very powerful graphics. We saw that there are different names given to different objects that we can specify in order for us to be able to come out with specific graphs. So today, we are going to continue from where we stopped. We drew a scatter plot yesterday, and we stopped on a scatter plot that has a smooth line. We drew this one. We also drew a scatter plot that has a straight line, okay? And so there are so many things we can do here. We can add R², we can do so many things, and we will continue ahead and see how we can do some other things in the interest of time. Now, today, we are going to start by adding color into the scatter plot. So the data set that we're using, again, is the crop recommendation data set. If you didn't import it yesterday, make sure that the crop recommendation dataset is inside your working environment. So we are adding color to the plot because we want to see if there are any clear patterns in the difference in low yield and high yield, okay? When we visualize the relationship between rainfall and nitrogen. We want to see, is the high yield happening when there is high rainfall and high levels of nitrogen, or is it scattered all over the graph and there is no apparent relationship? That is what we want to do. So in order to do that, you specify the color in the aesthetics function. So we say that the aesthetics part of the ggplot is where we can specify a change of color, or you can categorize basing on a given variable of interest within your data set. So in our case, we have chosen the yield category, and this is how our visualization looks like. So we will go to RStudio and do that, but we can go through two different graphs. You can also add a smooth line in this so that for each category, you see the movement in the relationship of those variables, or the relationship between nitrogen and rainfall for each category of yield. Okay, so these have already been classified. You want to see if there are any obvious differences. And so we should be able to draw this. And the way you do that is by adding the geom smooth onto, as a new layer, onto the existing graph that we have already created by adding the color onto that graph. And then the other thing is you can also specify a straight line for both relationships for the different categories that you have on the same graph. So each of these is done by adding a layer onto the ggplot function. And then lastly, you can create a facet of the different graphs. You can separate the two, the high yield and the low yield, on two different facets of your graph. You can transform this into horizontal, etc., depending on what you want to see. Okay, so it's important that you know which layer adds which part of the visualization onto the diagram that you want to see, or the figure that you want to see. So it's also important that you are able to run this and actually come up with these figures and be able to interpret them correctly. So at this point, let's draw these graphs here. Let's draw the graphs. If you still have your graphs of yesterday, you can check them out using this arrow here. Okay, we should be having all the previous graphs that we drew. You can clear them. You can export them. That was the last thing we tried to do yesterday. So today we are starting from here. Meanwhile, when you start by loading libraries. Every time you're working with existing code, the libraries are important. Where you see the library function, you load the library so that in case you need the functions along the way, you can use them. So remember that you load the libraries, you can highlight them and click on run here. This one here, okay? I'll make sure that you have run all the libraries. I'm also assuming that you have the crop recommendation data that we used yesterday. Make sure you can see it in your environment. If you cannot see it, you use this code, the read_Excel, to import it so you can have it in your environment. Also, you use the read_Excel for the Kenya Agri Disease Special Data Set, so you can have it here. Now, I already have both, so you run these two lines if you don't have that already. So today we are looking at ggplot. So the ggplot functions are down here. Yesterday we stopped at adding a straight line, which would be this line here. So remember also that we put comments within our R script so that you can understand what the code is doing. Now, if we didn't have comments here, it would be confusing. You would probably not know where which code stops. It would take a lot of time trying to navigate the code, okay? Basically also because if you're not the one that ran the code, rather if you're not the one that wrote the code, for example, but you're using it, it may be difficult to understand the workflow of the person that provided the code. Now, if you're collaborating on a project, for example, and you're writing different sections of code, it's important that you document your code using these comments here so that people who are using the code can quickly understand what your code is doing. I mean, with practice, you would probably be able to know what the code is doing, but it's good practice to also sort of document your code. So we are here adding color. And I already added color to mine. That is why I have this, okay? I already added color to mine. That is why I have this. And now, for the rest of us, let me know if you have color. Which line is the code? Line 104. from line 105. From line 105. In this code, it's from line 105. If you have not added anything onto your code, you can go to line 105 under the comment, add color. That's where we are, right here. And if you've succeeded, type yes. Today we are going to do the exercises within the session. It's important. And then we can have one later. Okay, so yes, for those who have succeeded in drawing and adding color onto the scatter plot. Now you're going to do the exercise immediately after this. I want you to add color onto this scatter plot, basing on the different crops, basing on the different crops. Okay, so what does that mean? It means that you are going to write a ggplot function, okay, that has the crop variable instead of the yield category. We want the color by crop, and then you run. So what I want you to do is, I mean, you can type this code, but to make your work faster, copy the code and under your exercise, change the color instead of using yield category. I want you to draw the color by crop. This. Okay, so this is it. So then I want you to run this and let me know if you succeed in drawing a scatter plot in which the points are differentiated by different colors for different crops. Different colors for different crops. Yes, if you're succeeding. No, if error in ggplot. So Aaron, you have an error in ggplot because you did not load the library of ggplot. And this is where it is. I didn't put it up. Yesterday we were explaining. So it's somewhere up here on line 79. Load the library ggplot2 so that you can access the function ggplot. So that you can access the function ggplot. Whenever you get an error that says the function is not found, it's because the library that contains that function has not been loaded. So you need to look for that line of code. So we have it here. Actually, we can just remove it from here and put it up so that all your libraries are loaded at once when you start. It doesn't matter where it's located in the script. I've just put it there so that we can always load it. Okay, now the exercise, we are here in the exercise. So what I wanted you to do when you have created the scatter plot, the exercise is that we want you to, instead of differentiating the colors by the yield category, we want you to differentiate the color by the type of crop. So that means it's the same ggplot function, but the color you specify the crop variable so that you can see different colors for different crops. If you have succeeded, type yes, done, 1, complete, successful for us to see. So I haven't run mine. Let me try it. Okay. So mine is also successful. Different colors for different crops on this graph here. So when you look at this, you want to see if there are any obvious differences. If there are any obvious differences, for example, which crops generally need higher rainfall, which crops need lower rainfall. So you see that the points for some crops are higher on the graph compared to others, okay? So you can quickly understand, for example, here, sugarcane needs quite a bit of rainfall and also nitrogen levels. We have the chicken pea here. It thrives well in low rainfall, okay, and low nitrogen conditions as well. So the graph, if you add color, you can see patterns that you wouldn't have seen, okay? Remember, we initially had a scatter plot, this one here. Maybe one that doesn't have colors, for example. So you can't tell. The only thing you can tell here is that there is a positive relationship between rainfall and nitrogen, higher rainfall, higher nitrogen. That's a positive correlation that we can see on this graph. However, you can add layers like we've done now with the crops, so you can be able to see if there are any clear patterns. And in this case, we see some very clear differences between the level of rainfall for the different crops here. So it's important that you see this and you're able to pick out some patterns. Okay. Let me see. I see a comment here. Path does not exist. So if your path does not exist, it's because you are not in your working directory. You're not in the data science folder. That's one. Or your RStudio that you opened was not the actual project that we are dealing with. So please make sure that you are able to access that. Alternatively, for the person who is not seeing there, you can import it from here. Just import the data from here. Import the data from here. The person is using crop data. We are going to use the crop data as well. Both the crop data and the recommendation data as well. Error in geom point. Crop not found. Did you load the library of ggplot? Try loading the library of ggplot up. Now I removed mine, but it's supposed to be somewhere down. You will find it just before we started here, around this line here, between 77 and 79. You should find a library of ggplot. I moved mine up here so that it would be easy to see and load that library there. So you need to load that library so you can be able to access the functions for ggplot.
Please, somebody's asking for you to repeat the exercise in the Q&A.
Okay. So the exercise, somebody has a zip file.
And
So
then
the
also
exercise,
somebody is also asking to interpret the graph of the rainfall and nitrogen. Thank you.
okay, so we are going to do both. The exercise is here. First of all, make sure that we are working in the same code, okay? You can type within the code, but we need to follow exactly where we are. So right now, we are adding color to the scatter plot that we have. And so when you run this particular one here, you should differentiate the points on the graph by yield category, okay? Specifying those that are high and those that are low. Now the exercise is, instead of introducing the color or seeing the points differentiated by color by yield category, would like you to do that by the type of crop instead on the same graph. And how do we do that? It's the same code, but now you specify the color by crop. Specify the color by crop so that you can have your points on this graph here differentiated by color. but the colors represent the different categories of the crops that we have. At this point, the colors are representing the different categories, the yield categories, and there are only two. So that is the exercise. So I already copied my code from up to here, and I changed the color to this. So I expect you to run this. And after running, you should be able to have a graph that looks like this. Okay, now the second question is interpretation. Yes, so this is a graph that shows rainfall. So it shows the rainfall, low levels of rainfall, higher levels of rainfall, low levels of nitrogen, higher levels of nitrogen. The graph moves up on the y-axis and it moves to this side on the x-axis. So the fact that you are seeing the crop or the values here, it simply means that the values that appear on the higher side need higher rainfall, okay? So for example, here we have sugarcane. Most of the values are here. So it means sugarcane needs higher rainfall compared to, I made only two comparisons here. I made the comparison between sugarcane and chicken pea. You see, the thing with colors is that if you're colorblind, it can be difficult to differentiate colors on a graph. But you can see this for the sugarcane and this for the chicken pea. So that's the interpretation that I put there because this requires less rainfall compared to these values. Now the value for blue, which is rice, also requires high rainfall. So it means rice generally grows in conditions of higher rainfall and it is captured in the data set. But you see, if you look at the data set, you may not be able to identify those patterns until either you summarize or visualize. So it's easier when you visualize, you can quickly see which crops will need higher rainfall. When you want to make a decision, for example, away from where this data was collected, you will, basing on the information that you have, you see that there are crops that grow with high rainfall, there are those that are medium, and then there are those that thrive well in low rainfall. Okay, so now the graph, we've added color by crop. Let's go ahead to add straight line by category, by yield category. That is actually a smooth line. Okay, so you can add a smooth line for each of them. You can add a straight line for each category. And lastly, you can add the facets as well. Okay, so let me explain the reason why I am not highlighting the entire code, ideally like this, which you can do just so you are sure that you are running the code. But the ggplot function is one code that is connected by these plus signs here. And remember, each plus sign is adding a layer onto the ggplot. So it doesn't matter where you put that cursor. If you put it in the middle here, that code has to run. If you put it in the beginning here, the code will work. If you put it at the end, the code will work. So that is why sometimes I just place the cursor anywhere in the code. When you run, it should run the entire chunk of code right from ggplot to the very end. So you can produce your faceted graph like this. And you can also do this for the different crops that you have. So you produce a graph that has many different facets for the different crops as well. Okay. So before we do the next exercise, I'm pausing to see if you have successfully drawn the graph that has one, the straight line per category, This is a smooth line. You can edit that. And also the one that has a straight line and the one that has the yield category. So in other words, when you come here in your output and you try to go back using this arrow here, which shows the previous graph, you should see your graphs, okay? The ones you've been drawing. So I would like you to have this graph, this graph, this graph as well. And we give ourselves 1 or 2 minutes and we see if we are succeeding in drawing the graph. Yes, if you have the graph. Yes, if you have the graph. Okay. Why do I have an error in geom point? The person that has an error in geom point, can you confirm if you have loaded the library of ggplot? This line of code here that says library ggplot2, this one. Make sure that you run this line of code, run. And then let us know if you still have the same challenge with the function geom point. Let us know. Now Q&A, somehow I am not looking at the Q&A. Okay, somebody is asking, what is a facet? So facet is splitting the graph so that each category appears on its own. The points are differentiated in the different graphs basing on the category that you have specified. That is a facet. That is a faceted graph. All right, so we come back here and we are back to the facets, okay? I would like you to, the exercise that we are doing, and together, this is the exercise under the facets. I would like you to draw a graph that is faceted by crops, okay? So it means instead of adding a layer that produces a facet and specifying the variable as the yield category, you will specify the variable as the crop. Specify the variable as the crop and see if you come up with a faceted graph. Okay? Remember, you can either type the code or you can just carry the code from up here, copy. Under the exercise, you change the facet, the grids from yield category to crop. Let me know if it is successful. Yes, 1 for yes, 0 for no. You can also type the challenge. If you have an error term, you can just paste it there. Zero. Okay. Somebody has a 0. Let me see the error. Huh. The error disappeared. Let me try to find it up there. Okay, so okay, so the person who has this error that says error in combining the variables and the crop, the variable crop has a capital C in the what? In the data set. So I see that you have used a small c. Remember that R is case sensitive. So change the small c to capital C so that you can, right now it's not locating that variable called crop with a small c. That's the challenge. Okay. Okay, now it's working. That's great. There's another error here. Someone has the same error with geom point. Okay, so as we wait for other people to, they should change the color from, yes, the color from yield category to, okay, somebody says they're lost. Florence, where did you get lost? Okay, so the facet means we are splitting the graph so that the points that we are seeing are for different values of the categories that we have here, that we have specified, okay? So instead of having one graph that combines all the, let me scroll here, that combines all the yield that has been classified as high and low, when you do a facet, you differentiate them and put them on different graphs. Maybe it becomes easier for you to see the patterns of the two when they are on different graphs, but laid side by side together, so you can be able to quickly see if there are any differences. For example, here, the slope is not so different, so the relationship doesn't really vary a lot, okay, among high-yielding crops and low-yielding crops. I want to know if you've successfully done this, okay? And I want to see if there are any errors. Okay, so I think we are successful and we proceed. You will bear with us for now if we are moving slowly. Somebody says I should run it on my side too. On my side, my exercises here. Somebody says they can do crop by yield category. Yeah, you can do that. You can do that as well. So, I mean, you can try so many of these things. You can try so many of these things so that you are able to have clear differences on your side, because this is exploratory data analysis. So it simply means you can try and check for different relationships if you know the graphs that can be able to help you. Okay. Somebody says theirs are different. So let me run mine and see how it looks like. You need to, when you run, you need to zoom it. And there is something that we need to change. You need to change this to crop. Zoom and zoom again. Okay, so I see why you wanted me to run it on my side. So make sure that the color is also by crop. Now, when you leave the color to yield category, you add another layer where you can do a visualization trying to differentiate yield, high yield within the same crop, and different crops for different facets, okay? Okay, so you can also be able to do that. So try to change the color to crop and see if you have the same graph like I do. Change the color to crop. Change the color to crop and see if somebody says, yes, it's like theirs. Okay. All right, so let's move. We do have some time. Okay, so that is having faceted graphs. Now we move to box plots. We can have box plots as well. We can see the amount of rainfall as well for the different crops. We can visualize the box plot horizontally, but we can also visualize the box plots vertically. When you look at a box plot like this, so mostly box plots show distributions, but also you can see the median or the average rainfall that is required for each crop on this graph here that we actually saw as well on the scatter plot. So the ones that are higher, the ones whose median are higher, require more rainfall, okay, on average. So for example, rice requires more rainfall, then I think followed by sugarcane, then this one is, I think, coffee, then this green, I think is this one, maize, this is potatoes, and then wheat, and then we can have chickpea, I think, down here. So the box plot helps you to see those averages in a snapshot and compare them across different groups as well. Okay, so we can draw a box plot for one variable just to see the distribution. But you can also draw a box plot to see if there are any differences in the distribution within the different categories that you might be interested in. So we can quickly see if you have the same box plot. Okay. Meanwhile, when you run the code, the cursor automatically gets out of this code, okay, the entire code, and moves to the next one. So just run the first one, and then you can run them vertically. Sometimes it's easier to see, okay? These, if the categories are many, it's easier to see them side by side like this, okay? Where the rainfall is on the x-axis. And then the average rainfall, the different crops are here. Okay, like that. Then you can be able to quickly see which one requires more rainfall because this is average rainfall. As we've seen before, the box plot shows mainly the median, maximum, outliers if they exist, etc. Okay, so let me know if you have this figure, first of all. If you have this figure, somebody says they're requesting for PowerPoints. The PowerPoints are there every single day. You have the PowerPoints uploaded in the Google Drive. It's just that we upload them after each session. Okay, somebody says we repeat. All right, so we are repeating. Did you first of all draw this? Because I'm going to close mine. And so the box plot, okay? The geom point here is the geom underscore box plot. Pay attention to the geom points because rather the geom object, because the different geom objects specify the type of graphs that are going to be plotted. So previously, we've been using the geom point, this one here, and the geom smooth to add smooth lines. Now we have moved to the geom box plot because it's the one that creates the box plot, okay? We label and we remove some, we truncate just to make it easy for us to interpret this. And then also just to note that the layer that flips this graph here from this one to this one, that layer is called the code flip. So when you add the code flip layer to a geom box plot, you will have your boxes arranged vertically like this. By default, the geom box plot produces horizontal boxes. Okay. So I am still waiting for confirmation that you have drawn both. I can't see any data in my environment, but the graphs are successfully done. What do you mean the data? Because data in the environment is here, okay? Sometimes if you've expanded this beyond, you may not see your data actually. You can expand this thing like this. So if that is the case, then you need to bring back this so you can be able to see your environment. The other reason that you may not be seeing the environment is because you are either under history, and so what you're seeing is a history of the codes that you are running. They come here to your under history, okay? And also, I mean, you could be anywhere here, but not under environment. So make sure, first of all, that you're under environment, and make sure that this part is not covering the environment, because if it covers the environment, the codes will work because it will access the data, but you will not see it simply because this is not there. Or you might only have one window. And if you have one window, it means you need to display the environment window by clicking here. Then it will go back. Now mine has gone away with this window. Okay, so you can bring back your window there like that. I can't see the difference between the script of horizontal and vertical plots. The difference between the horizontal and the vertical plots is here. The difference is that this one has a layer, a new layer, this one here. If you notice, this layer was added so it can flip the graph. Up here, we don't have that layer. After labeling, we just add the theme. But here, we add the code flip so we can flip the graph to the horizontal. Okay, so let's proceed if we are successful. Let's proceed if we are successful. Back to the PowerPoint. We are moving to the next graph. In the interest of time, we are moving to the next graph, and the next graph is a histogram. We've drawn the histogram before. We have drawn the histogram using the histogram function. There is a function that draws a histogram. Even in base R, there is a function that draws the box plot. It's just that you can use that function, but you can also use ggplot. When you are drawing a histogram in ggplot, you specify the geom object. This one has the geom underscore histogram, and also specify the variable. Remember, the histogram helps us to visualize the distribution of a numerical variable, one numerical variable in the data set. So, for example, if you want to understand the distribution of yield per kilogram per hectare in the crop recommendation data. Then you need to specify the object as the histogram and draw the histogram. I mean, clearly we can see that this distribution is not normal, it is skewed to the right, okay? You can also add the density plot onto the histogram, and you can still see and note that it is not normally distributed. Now, with normal distribution, for you to be able to confirm that a variable is really not normally distributed, you also need to perform the statistical test associated with it. And we are going to look at the test. We've looked at it before, but now we will look at it as we see the hypothesis behind the test and clearly make decisions as to whether the variable is normally distributed or not normally distributed. So you can draw your histogram first. Draw your histogram for the crop yield. Produce the normal distribution curve, superimpose it on the histogram. Superimpose it on the histogram. And we are going to do an exercise here. We are going to do an exercise in real time. So I didn't type it there, but you are going to type it. Okay, under this, draw a histogram. And you're drawing a histogram for, where is the crop recommendation data? You're drawing it for rainfall. Draw it for rainfall. Let's check if the rainfall seems to look normally distributed. Draw a histogram for rainfall. So in order to do this exercise, what you need to do is to get this code here under histogram, this one. Okay, that's the code you copy. And under here, where you have typed your exercise, you change the variable because now we want the variable for rainfall. Change the variable to rainfall. Draw your histogram. Let us see. Draw your histogram and let us see. Okay, warnings do not necessarily prevent your functions from running. So that should be okay. So does it look normally distributed? When you succeed, type yes, 1, or done. Okay, I see that we are succeeding. I see that we are succeeding. Okay. So it's skewed to the left. Somebody saying theirs looks normally distributed. Skewed to the left. All right, it looks like we are succeeding. Okay, so the histogram for rainfall should look like this. It looks like this. And it is not normally distributed. It is skewed. All right, so we can proceed. It is not normally distributed. Let's just proceed. So we move to the next graph, which is a bar graph. Now, bar graphs are pretty common graphs that we use. We use bar graphs to show the different, usually the count in different categories of information that we have in our data set. For example, you might want to display from a frequency distribution table that contains how many crops or harvests have been reported as of high yield and low yield. Okay. Now, it is that information on a distribution, a frequency distribution table that you can display using a bar graph. So really the bars are showing the different categories. The height of the bar is showing the number or the frequency itself for that particular category. Again, when you're looking at geom, the ggplot function, you see that the geom object is the geom underscore bar. So the geom bar is the one that produces a bar graph, okay? The geom bar is the one that produces a bar graph. So the geom bar can also be used to produce a component bar graph. A component bar graph is that graph where the different bars have different components of another, for example, variable. So it's more of a display, a representation of a cross tabulation. If you have a cross tabulation where you have two variables, you want to know how many are in each category, okay? Then you can display that information on a component bar graph. For example, here, we have, ideally, this information comes from a table, a cross tabulation, okay? How many crops have been reported or how many yields have been reported to be high from the different crops that we have. So you can easily see that within each, how many would you have? So this is trying to represent some sort of cross tabulation. If we've drawn a cross tabulation before, we are going to go back to R and draw a cross tabulation and see what we are talking about here. That the component bar graph basically shows us across the information that would be displayed on a cross tabulation, okay? And to introduce the components by different categories, we fill the bars, okay, by the variable that we want to display. We fill the bar by the variable that we want to display. In our case, it is the crop. That is why we fill this by the crop. So this graph here can be flipped as well, okay? You can flip the graph so that you can display it like this horizontally. And the layer that does this again is the code flip layer. You see, this is the same layer that we added to the box plot function. It is the same layer that we add here if we want to flip this graph as well. So let's go into R. We are going to draw the graph, but we're also going to draw that cross tabulation together. It's not here, but you will be able to draw it. First of all, draw the bar graph itself. Let's see if you can produce the bar graph. I'll just pull this up by crop. Make sure you can see your bar graphs. You can flip and we see if you have the horizontal one as well. Now, I want to produce that cross tabulation that helps us to produce component graphs that look like this. So you can use the table function as we did earlier. We are using the crop recommendation data and we reference the variable crop. And also we reference the variable yield category. And draw. So this here is the cross tabulation that is being represented here. So under the high, okay, we are seeing how many observations are being observed from each of the different categories or different crops that we have in the data set. And then from low, we also see how many they are. And then we represent it here. I mean, if you do this, you probably see it much better. like this. So do the cross tabulation so that we can see the information, so that you can know what a component graph really represents. It is representing a cross tabulation that looks like this. So I would like you to draw, first of all, the bar graphs, then use this table function. You're going to have to type it, use the table function to produce the cross tabulation for crop and yield category. And yes, if you've succeeded. No, if you're having a challenge, you can type the challenge right there. You can type the challenge right there. You can type the challenge there. Somebody says they had internet. Drawing the graph. If you've succeeded, you can put your output here with high and low, and then the crops. If you had an internet challenge, we are here under the graphs, the bar graph. Run the first one, the geom bar will produce the first one by yield. The second one will produce a component bar graph by crop for the different yield categories, okay? And the last one will produce the same component graph, but it is a flipped graph, but it shows the different components. And then the cross tabulation that summarizes this information that is put on this graph is got using the table function. And you can also have the table function here. So I would like you to draw the table function. And before we proceed, let's see if we are succeeding. Yes, yes. Okay. Just put the output there. Just put the output there. Yes, we can also have percentages. Unexpected error. That error is coming because you did not put that error is coming because you didn't put, if you're seeing you did not put the comma that separates this, okay? There should be a comma that separates the two inside the table function. I see that you don't have it. So you need to put it there. After crop recommendation, $ crop, then you put a comma, then crop recommendation, $ yield category. Yield category. You should, that error should go away. That error should go away. Okay. Looks like we are succeeding. All right, so let's proceed. So there are so many graphs that you can produce with R and ggplot2 in particular. So there are many geom objects that come with R. It is important and good that you explore them. There are completely complex graphs that we can also produce with R, and we shall see them as we go forward. But it's important that you know that there is a function, a package ggplot2 that can be able to produce these graphs for us so that we can be able to understand them. Okay, now, what we've been doing, okay, is describing information, more of descriptive analytics. Now we are moving to diagnostic analytics. And in diagnostic analytics, we want to see relationships. We want to test hypotheses. We want to ask questions. We want to know if there exists relationships. We want to see if these relationships are significant, okay, within and among the variables. So that is what we call diagnostic analytics in data science. And that is the section that we are moving on. And when we talk of diagnostic analytics, we need to understand the concept of hypothesis. Hypotheses are important because all the tests that we do based on certain hypotheses, and making decisions in data science bases on interpreting the hypothesis and determining whether the relationship is true, and hence answering a research question. So it's important to know what a hypothesis is, what it does, and when you are performing a test, in the back of your mind, you have and know the hypothesis that you're working with. And the decision-making process is standard when we are dealing with hypotheses. So we're looking at hypothesis and we are describing what it is. So it is a claim and about a single value of a population characteristic, or several of them, as we are going to see. So what does that mean? It means that you have prior information, or you think you have prior information, maybe from existing populations, okay? So that is the claim that you have. But in order to prove whether that claim is true or not, you have another alternative that competes with the null hypothesis. And the issue is, how can you prove that the null is either true or not true? So if you have an alternative, then you need evidence to show that the alternative is true. And that evidence is what you get from sample data if you have information. So the data sets that you have, you want to use them to find evidence to either support your null or support the alternative. So it's important that you know that the data that you have, you need to find a way of extracting information from there so that you can make a decision that is guided by a scientific approach and method, which is hypothesis testing. So testing a hypothesis means that you are going to use the data that you have so that you can decide on whether the null hypothesis or the claim that you know or you have about the population is true, or the alternative that you have is the one that is true. Okay? These are scientific procedures, and we are going to see how to make decisions basing on hypothesis. So one thing that you need to do is make sure that you have the null hypothesis. So the null hypothesis is a statement that and a claim that you have, and the alternative is what you think it should be, or what you think you are collecting data for in order to prove. For example, you can have a null hypothesis that says the average yield of maize is 6,000 kilograms per hectare. And that is because you probably got this information from previous harvests, for example. So first of all, you can generate your null hypothesis from prior information, or from a sample, a small pre-survey that you've done, and you think that that is what is existing in the population. However, the data that you collect can quickly tell you whether it is not true, okay? So the yield can easily be greater than 6,000, for example. It could be less than 6,000, or you might just be simply interested that it's not equal to 6,000. Now, this hypothesis here is for an agricultural data set, an agricultural domain. But you can also make the hypothesis for different domains, okay? In health, in human resource, in finance, you can have null hypothesis and would still follow the same procedure to check whether the alternatives have, if there is enough evidence in your data set to support the alternative or to support the null that you think you are working with, the one that you have got from prior information from the population. So that also means that null hypotheses are stated basing on what you think is happening in the population, not in sample data sets that you have. Okay, so how do you do the hypothesis testing? One, as we've seen, you must have a null hypothesis, okay? Two, there should be alternatives And the aim is to see if you have evidence, okay, to show that the alternative is either true or not. Okay, so that means you must have a data set. You must have information you're going to use to either support the null or support the alternative hypothesis that you have. Okay, so it also means that there are only two decisions you can make. Either you reject the null because you have enough evidence to support the alternative. If you have enough evidence to show, for example, that the yield is greater than 6,000, then you can say that, okay, the yield is not 6,000 because according to the data that I have collected, I have enough evidence to make this conclusion, okay? You can also fail to reject the null hypothesis. What does that mean? It means that according to the data that you have, you do not have enough evidence to say that the yield is not equal to 6,000. Okay, the maize yield is not equal to 6,000. That's the average. So the two decisions that can be made when you are performing a hypothesis testing procedure will lead you to either accept the null or reject it. Okay, obviously, when you accept the null hypothesis, it means you're not taking the alternative. But if you have enough evidence and you reject the null, okay, which you thought was true, then you will take the alternative. That is how we make decisions. But also, how do you conclude and say that the null, you have enough evidence to accept the null, or you have enough evidence, for example, to reject the null? We use p-values. P-values help us to make decisions. It's important that you make the correct decision basing on the p-value. These are probability values. So small p-values provide strong evidence against the null hypothesis. So when you have a small p-value, you will be able to say that I have enough evidence to reject the null. But if the p-value is great or large, okay, given a threshold, then you do not have enough evidence to reject the null. So you will accept the null because the data that you have does not have enough evidence to support the alternative that you are claiming. And what is that value? Okay, when do you say that P is small or P is large? Therefore, you do not have strong evidence against the null hypothesis. So conventionally, we use 0.05, okay, such that if p-values are greater than 0.05, you tend to accept the null hypothesis. Remember, small p-values provide strong evidence against the null hypothesis. So if the value is big and we are saying a threshold needs to be available for you to make the decision, and conventionally, we use 0.05 as the threshold so we can be able to make appropriate decisions. For us to make decisions, you see, these decisions that you make here will translate into decisions that you make in your organization because you have evidence to prove, for example, that the null is true or it is not true. Okay, depending on the null that you have stated, depending on the problem that you have at hand. So it's important that you collect data that is usable, that can be used for you to make these decisions. There are other levels of p-values that we can use, but conventionally, we shall be using 0.05 as the point to make decisions whenever we are doing our hypothesis testing. So the issue now is, what are those? Okay, we can do the interpretation. I mean, this is what I've been explaining, okay? A value like 0.27 is big, is large, is greater than 0.05. So it doesn't provide evidence against the null, okay? So it simply means you cannot reject the null. You have to accept the null hypothesis. But now, a value like 0.01 is less than 0.05. And we said small p-values provide strong evidence against the null hypothesis. So a p-value like 0.01 will make you to reject the null hypothesis. Likewise, a p-value of 0.04 will also lead you to reject the null hypothesis. It's just that one is significantly higher than the other in terms of evidence against the null hypothesis. So from now on, for every statistical test that we perform to make decisions in data science, we need to correctly interpret the p-value. We need to correctly interpret the p-value. So what are those tests that we have? We have different tests. Again, if I summarize the hypothesis, it's the same thing we've been saying. State the null and the alternative. Specify the null distribution like we did, okay? The yield is 6,000. Collect data. We already have data sets that we are going to use to test this hypothesis. Calculate the p-value. Yes, we are going to calculate the p-value. You don't have to calculate the p-value by hand. I mean, we have all these tools that help us to calculate the p-value, but it's important that you interpret the p-value correctly so that you can make a decision whether you want to reject or to accept the null hypothesis. Okay, so these methods that we use for hypothesis testing are generally divided into two. And when I say divided into two, there are methods which are parametric in nature, and there are methods which are non-parametric in nature. The difference between the two is that for methods that are parametric, we use them when the variables that we are dealing with are normally distributed or approximately normally distributed, okay? So when you have normally distributed data, even the methods of central tendency that you choose should be parametric, for example, the mean. The methods of dispersion should also be parametric, for example, the variance. But when you have data that is not normally distributed, we use non-parametric methods to perform statistical tests. So it doesn't mean that if you have non-normally distributed data, you cannot perform a hypothesis test. You can. You just have to use non-parametric methods that do not rely on distributions. Okay, for example, if you are summarizing, you will use the median because the median is a non-parametric test, rather approach to understanding the central tendency of a data set. Okay, we shall see which tests are considered parametric and which tests are considered non-parametric. The challenge is if you use a parametric test in a situation that requires non-parametric tests, you're not sure if the p-value is correct. So you're also not sure if the decision you are making is also correct. So it's important that you pay attention when you are choosing tests. And if the data is not normally distributed, you can transform the data if you really want to use normal distribution or parametric tests. And we shall see what they are and how we are going to do that. So we start from here. There are many hypothesis testing methods, okay? And when data is normally distributed, first of all, you can summarize the data using the mean, the variance, standard deviation for normal distribution. On this side, you can summarize the data using the median, using the rank, using ranges for measures of dispersion, using interquartile ranges for measures of dispersion. Now, in parametric methods, when data is normally distributed, you can perform things like the t-test, because the t-test tests for equality of means. And here is where we use the mean, for example, to summarize parametric data. The ANOVA also tests equality of means when you have more than 3 categories. On the other side, non-parametric methods are used when you have information like the median. So, for example, the Wilcoxon's rank sum test will check if the medians are similar. The Kruskal-Wallis will test if the medians are similar when you have more than 2 categories. So in other words, the Wilcoxon, for example, is an equivalent of the t-test when you have non-normally distributed data. Kruskal-Wallis test is the non-parametric approach for the ANOVA test. And we're going to see the situations and how we can do this. So when you're making decisions, the choice of the test also matters. The choice of the test also matters. Okay, and because the choice of the test matters, we have a very important hypothesis procedure that is used to test for normality. We have been using it, and sometimes we are confused. Why are we saying that it is not normally distributed? Why are you concluding that it is normally distributed? Now that is a hypothesis testing procedure, and we need to now know why we make these decisions. For starters, you must know what the null hypothesis is when you are dealing with the test for normality. This particular one is the Shapiro-Wilk test for normality. So the null hypothesis, when you are testing for yes?
Please, somebody wants you to explain the null hypothesis, because I think they're lost right from the beginning. It didn't get clear what it means. Different between null and alternative.
All right, so let's explain the null. Let's go back here a bit. So we'll just make a recap here. So I want to go back a bit, I think. So we'll explain what the null is. And then we go back. So the null hypothesis is a claim about a population characteristic. So you claim, okay? You claim that you think something is happening in the population, and then you check from the data that you have whether that is true or not. The example I gave that says the yield is 6,000, that's the null, that's what we are thinking. But the null can be a statement. It doesn't have to have an equal sign or something like that. So the alternative is something that competes with the null, for which you want evidence to know whether it's true or not. And for you to come up with a null, you need to have prior information, but also interest in what you are studying or the research question that you want to answer. So in our case, now, our null hypothesis, when we are looking at, for example, this test that we're dealing with, where we were here, we have a null hypothesis that says that the variable, okay, is normally distributed. But we also have an alternative that says it is not normally distributed. So what we want to do, we want to test and see if this is true. So we want to run a test, okay, and get a p-value and use that p-value to do an interpretation. And we say that in order for us to do an interpretation, we need to know the p-value. You can only make a decision as to whether to say the data is normally distributed or not, basing on the p-value that is generated by the test procedure. Okay, so in a test like Shapiro's test, this is the null hypothesis. The alternative is that it's not normally distributed. So if your p-value is small, okay, you're going to reject the null hypothesis. But if your p-value is bigger than 0.05, then you do not have enough evidence to reject the null hypothesis. So what does that mean practically? It means that when you perform the Shapiro's test, for example, here, okay, we've been performing the test. This test here is trying to check if the yield is normally distributed. That is the Shapiro's test on the yield. So when you perform the test, you get the p-value and use the p-value to make a decision. Okay? Use the p-value to make a decision. So are you able to perform the Shapiro's test is the real question. So if you want to make a decision from here and you want to perform a test on Shapiro's test, we've done Shapiro's test many times. So here we have the test. And this test is on the yield. Remember also that the test for normality is done on variables that are normally distributed. So you run and check the p-values. It's important to pay attention. So we have a p-value here that is significant. This is a very small value with very many decimal places. So it means this is significant. So you can reject the null. And in the exercise, which we are going to do together, can you check if rainfall is normally distributed? What does that mean? It means perform the test on rainfall. Okay, where you see the yield, you perform the test on rainfall. Check and see if it is normally distributed. So the concept behind this is that you can interpret the p-value and make a decision. And then once you make the decision, you can proceed. All right, so somebody has results here. Run the test, put the results on the chat. Let me know if you've succeeded. Okay. So the value looks significant so far. The value looks significant, highly significant. I'm trying to read. I saw some question. Let me try to scroll back. I can't seem to get the question. Somebody asked a question. Is it necessary to is it necessary that the null hypothesis should be a negative statement? The null hypothesis is usually a positive statement. It is usually a positive. Somebody says, but how should we change to other ways? What do you mean? Other ways? Other ways means you're probably asking if you need to display it differently. because when you display the p-value with the exponential, those are, for the negatives, those are the number of decimal places. And once there are many, then you're able to. Meanwhile, can somebody also type there what your interpretation is? So the question is, if it is significant, you reject the null hypothesis and you conclude that okay. So I see answers. When you reject the null, it is not normally distributed. When you reject the null, it is not normally distributed. So that is correct. Not normally distributed, not normally distributed. Yes. Can you try one more test here? One more test is in the crop data. Can you test the pH? The pH, this one here, test and see whether it is normally distributed, the pH. Okay, so instead of rainfall, we are testing whether the pH is normally distributed. P with capital H and small p. And let us know. Okay. So the p-value is small. So it provides evidence against the null. You reject the null hypothesis and conclude that it is not normally distributed. I hope everybody has the same p-value. So I'm trying to look. P-value is small. P-value is small. Reject H0. Okay, so that is correct. Let's proceed. And we are moving to the next test. So the Z test is a test for normality. We are now looking at the T test. The T test is a test for equality of means, okay? Equality of means. So it checks whether the mean of one group is the same as another group. And you perform the test, check whether the p-value supports the evidence, and you make an appropriate conclusion. And how do you do that? Because it tests for equality of two means, the null hypothesis will always state that the two means are equal. So mean for group 1 is the same as the mean for group 2. And then the alternative is that the two means are not equal. Okay? You can perform the test and then after make the conclusion as to whether the two means in the two groups are the same. So let's do that very fast. We are going to perform the t-test in the Kenya spatial data and see if the pesticide use per kilogram is different in the different years. Now, the Kenyan data, where is mine? This one here, has the year 2005 and 2025 and then 2024. So perform the test. I would like you to run this test and see. Make sure that when you're performing the t-test, that categorical variable has only two categories. It has only two categories because the t-test is designed for checking the mean in two categories or two levels. So the outcome is here. The pesticide, okay, in kilograms by year. So because we are testing equality of means, it will also give you the mean in one group and the mean in another group. So these two look similar, but we want to be sure that they're actually either similar or they are not similar. So that is why we perform the t-test. So ideally, the t-test is checking whether these two are similar, okay, statistically. And so now we look at the p-value, this one here, this value here. And according to this p-value, now I will be asking a question so you can type in the chat. Do you reject the null or do you accept the null? Is the p-value small or is the p-value big? The p-value is 0.6412. Okay, so somebody says we reject the null. Somebody says we accept the null. Okay, fail to reject. Reject. Okay, so the p-value is big. So we don't have enough evidence to reject that null hypothesis. So we accept the null hypothesis. And when we accept the null, we conclude that the means are the same. Okay, we fail to reject, we accept. All right, so it looks like we are able to interpret the p-value correctly. So we can move to the next. Okay, so that is the p-value, the t-test, this one. Now we move to the ANOVA test as well. So we have an ANOVA test as well. What is the ANOVA test and when do you use the ANOVA test? The ANOVA test is used when you have more than two categories in the categorical variable and you want to check whether the means are equal as well. Okay, it does the same thing with the t-test, but here we use when we have more than two categories. So ANOVA is used to determine differences between results from 3 or more unrelated groups, which is what we've said. Okay, so first of all, the information from the groups should be independent. That is one. And ANOVA is a parametric test. So it also means that that variable whose mean you want to check, okay, across the different categories should be normally distributed and have similar variance. So how do you write the null hypothesis? The null hypothesis is that the means of all the groups are equal against the alternative that they are not equal. I mean, you could state it by saying the population mean for the first group is equal to that of the second group up to the last one. If there are 5 groups, you're probably saying the mean of the first group, which is mu1, is the same as the second, the third, and the fourth. You can just write it by saying the means of all the groups are equal. And the alternative is that they're not equal. Now you want to get evidence from the data basing on the p-value to see if you can reject the null or if you can accept the null, okay? That is what ANOVA can do. There is also something else that ANOVA cannot do. ANOVA cannot determine which groups in particular are different. If you're saying the mean in group 1, in group 2, group 3 are not equal, and that is what you have concluded, ANOVA cannot tell you which 2 are different. So if you determine that they are not, then you perform other tests that will be able to show us which ones are different in particular. These tests are called the post hoc tests, okay, of the mean. And it helps you to determine which 2 groups are different when you have many groups and the ANOVA test has shown that they are significantly different according to the key value. How can you perform the ANOVA test? We have different levels of ANOVA. We have one-way, which is what we are looking at. We also have two-way, three-way, repeated measures. We shall look at them as we go forward. So an example would be pesticide use in the different soil types. Okay. Now we are using ANOVA here because we have 3 different soil types. We have the loamy, we have sandy, we have clay. Okay. So we cannot use the t-test. Then we extend it to ANOVA and perform the test. So the ANOVA test, we can use the ANOVA function. We can use the linear models function. Our interest is to be able to see the p-value here. You see this p-value? It helps us to understand whether we can reject the null or we can accept the null hypothesis. So in our case, basing on this, we want to see if we can be able to perform the test itself. So let's go here, perform the test, and would like to know if you can actually interpret the outcome of the test. Okay, so we are looking at the difference in pesticide use for the different soil types. So in other words, we want to know if the mean pesticide per kilogram varies across the different soil types. So here we'll use the AOV function, analysis of variance function, and then we summarize the function and obtain this p-value here. Okay, so the p-value is what helps us to either conclude that the means are the same or they are not the same. So basing on this p-value, do you accept or reject the null hypothesis? Basing on this p-value, do you accept or do you reject the null? Okay. Do you accept? Do you reject? Do you accept or do you reject? Type in the chat if you accept. Okay, fail to reject, accept. Fail to reject. Reject the null. Okay, so since it is greater than 0.05, ANOVA not found. Let me see. Somebody's saying they have not found ANOVA. ANOVA not found means you did not run the ANOVA. You see this line here? You need to put the cursor on the line. This is not one line of code because there is no addition sign. These are 2 separate codes. So you cannot summarize ANOVA when you have not created it. So using the AOV function, make sure that you have run both lines, this one here, to create the object that contains the information, the result from the ANOVA test. Then do the summary so you can display. Yes, you can also use the LM function, the linear models function. We are also going to use the linear models function as we go forward. That is okay. Now it works. Yes, it should work because now you have ANOVA in the environment. You have ANOVA in the environment. Pesticide not found. Where is the data set you're using? Make sure that the code to run, I highlight the code to run. It's here under ANOVA. Oops. Under ANOVA, we are I see that some people have challenges. Under ANOVA, run all the code under ANOVA. The first code will transform the soil type into a factor if you hadn't already done so. The second line of code will actually perform the ANOVA test and store it in an object called ANOVA. Then the last one they will summarize and display it here. So what I've highlighted is what you need to run. Somebody is saying fix the Kenyan data. What is wrong with the Kenya data? What is wrong with the Kenya data? Did you download the Kenya data from okay, now it's working for somewhere here. Did you download the Kenya data from the Google Drive? Did you download the Kenya data from the Google Drive? Do you have access to the Google Drive?
Please, somebody was asking if we have a test where ANOVA is significant so that we can perform a post hoc test. So in the Q&A.
Yeah, we can have that. If we have variables, we shall be able to do it as well. We shall be able to also show the post hoc. Okay, there is somebody that doesn't have the Kenya data set. Did you download it? Because if you downloaded the Kenyan dataset, then bring it to your environment here. Go to import dataset from Excel, browse, and find it Kenya. Spatial, open it. When it loads, import it into your workspace so that we can have this data here. Okay, and let us know. That is how you're going to bring the Kenyan dataset if you don't have it already in your workspace. If you don't have it already in your workspace. Yes, if you fail to reject the null, then it means, okay, somebody says they have it and have done it again. The same error. What is the error? Can you paste the error so I can see again? Paste the error so I can see. Paste the error. Okay, let's see. Make sure that the line of code that you have and the data is the same. This is alpha. Can you run the ANOVA function itself? Run the ANOVA function and a summary of the ANOVA function, and then you display it here. Okay, so you need to run the libraries. Where are they? Up here. Run the libraries up there, all of them, and so that you can find that variable. Run the libraries so you can find that variable. All right, so as you run the libraries, let's interpret the next one as we wait for feedback. Okay, so let's move to non-parametric approaches as well. We have Wilcoxon's test, which helps us to test if two medians are equal. So sometimes we call it the Mann-Whitney's U-test, and it doesn't require the data to be normally distributed. You can use ordinal data, and the null hypothesis for Will's test is that the medians are equal, and the alternative is that the medians are not equal. When you perform the test, you use the p-value to either reject or accept the null hypothesis. Either reject or accept the null hypothesis. So when the data is not normally distributed, like the rainfall data, okay, you can perform Wilcoxon's rank sum test to determine if the medians are the same. And you reject the null when the p-value is small. But when the p-value is large, like this one here, then you accept the null hypothesis. So perform Wilcoxon's test. Perform Wilcoxon's test. Somewhere down here, we use the Wilcox function as well. We use the Wilcox function. Okay, so you can just verify that rainfall is not normally distributed. Perform the test. Check whether average rainfall or median rainfall varies with the yield category, either high or low. And interpret the p-value. The p-value is here. Let me know if you, first of all, are able to run, but also whether you reject or not. Whether you reject or not. Do you accept the null hypothesis? Do you reject the null hypothesis? Do you accept or do you reject the null hypothesis? Okay, so somebody's saying accept the null. Now, if you accept the null, what do you conclude? What do you conclude? Because we are trying to make a decision as to whether the yield category, okay, the median rainfall is equivalent when the yield category is high or when the yield category is low. That is what we are trying to get. So are the medians equal or are they not equal according to this test here? Okay, so we conclude that they are equal. We conclude that they are equal. Okay, you are right to conclude that they are equal. Okay, there is no difference. That is correct. That is true. All right. No, it doesn't affect if they are similar. Okay, so we can proceed. Now we are here. We are looking at Kruskal-Wallis test. Kruskal-Wallis test will help us to determine if the median is equal in more than 3 different categories when the data is not normally distributed. So the null hypothesis, it corresponds to the ANOVA test basically because it works for more than 2 groups. And the null hypothesis is that the medians are equal The alternative is that they are not equal. Now, when you perform the test, okay, you check whether the p-value is significant. If the p-value is significant, then we need to understand which two groups are showing significance. Some may not be significant, others may be significant. Somebody asked that question earlier. So when you perform the test, first check whether you reject the null or accept the null. If you fail to reject the null, then the medians are really the same. But if you reject that null hypothesis, it means that the medians are not equal. And ANOVA does not tell us if the means are equal, and neither does the Kruskal test show us if the medians are equal. So what happens is after that, you need to perform the multiple comparisons test to understand which two groups or which groups could be different. So we are going to perform the Kruskal test to check whether different crops, okay, require rainfall at different levels. So we want to know if the median rainfall is really different, recorded for the different crops that have been captured, the yield in the data set. So that's what we want to do. So Kruskal's test is here. You can first make sure that your crop data variable is transformed into a factor. Then run Kruskal's test, and you will find Kruskal's test here. And then we explain what happens if there is a significant difference. So Kruskal's test, the p-value, somebody is saying, meanwhile, please perform the test, Kruskal's test. Somebody's saying they don't have the script. I don't know which script you're using, but the script you're using is here, data science code _1. If you're using another script, data science code, probably without the _1, then you're using a script of yesterday. Then you need to get this script from the Google Drive, which we did at the beginning of today's class. So please get it. It's the one we are using. It has all this. So please type there the p-value and whether you reject the null or not. It is significant. Yes, confirm whether you are rejecting the null hypothesis or not. Confirm whether you can reject the null. All right. So the medians are different. If you're rejecting the null, it means the medians are a bit different. So, but this test cannot tell us which crops, okay, are having significant differences in the required rainfall in terms of the median rainfall. So we perform what we call the post hoc test. The post hoc test, back to the slideshow, the post hoc test should let us know, okay, whether this is different or not, which ones are different. So we perform the test using the FSA package. So we are performing Dan's test, okay? It is a post hoc test that we perform when Kruskal-Wallis's test is significant, showing significant differences in the groups, meaning that the medians are different, but we don't know which ones are different. So it does the comparison now for in the group. Because we are using the crop, it will compare every pair of crops, compare the median, and produce a p-value, okay? P-values that are small will show significant differences. The ones that are not small will show that those two are not different. So for example, because this is a multiple comparisons test, it will do pairwise testing, starting with chicken, pea, and coffee, chicken, pea, and cotton, coffee, and cotton. So by the time we are done down here, we have at least compared 2 crops, at least each crop with the other, okay? And then we want to see where are the real differences if the Kruskal-Wallis test is showing that some groups are different. So when you look at the p-value, meanwhile, it's important that you interpret the p-values correctly. So significant p-values are small p-values less than 0.05. They indicate significant differences in those 2 compared groups. Okay, the median rainfall needed for these crops or observed in our data set. So this value, for example, is very significant. So we reject the null, conclude that they're different. This p-value here, on the other hand, with a E positive is a very big figure. So it's not significant. Okay, this one is way beyond 0.05. This one here, the second one. So it simply means that we don't have enough evidence. So they remain the same. This one is also very significant. Okay, is greater than 0.05. This one, the next one, I'll just stop somewhere, but this one is also significant. You reject the null. This one is not significant. This one has only 1 decimal place. Remember, our cutoff is 0.05. So 1 decimal place is way below 0.05. So this one is not significant. This one is significant. This one is not. This one is. This one is not. So you interpret them. You can now make the comparisons within the same. So let's make sure that you can actually do that and have it. Meanwhile, the test comes from a package called FSA. So install the package first if you have not installed it. That's why I put it down here. Install the FSA package. Those who installed it earlier don't need to install it again, but you highlight and install. I am not going to install it because I already have the package. But if you don't, highlight and run, then load the library of the FSA package, okay? And perform Dunn's multiple comparison test. And make sure you can see the adjusted p-values for each comparison, each group, to know which ones are really different. Let me know when you succeed. So I'll be asking a question and you will be giving answers. First of all, did you succeed in running the test? Is question 1. Then you can confirm in the chat. Okay? Yes. So let me see. Somebody did not find Dunn's test. Load the library. Install the what? Install the package FSA. Make sure you don't skip that line that installs the package. Crop was coerced to a factor. Yeah. It's supposed to have been transformed into a factor with the as.factor function. If it does that and coerces it, that's okay. So yes. Now the question is, if you succeed, somebody says, can I show the question in my console? Oh, okay. So I guess you mean, maybe, let me try to. Oh, I have not yet.
Please, somebody's
yes?
asking you in Q&A, why do you do those multiple comparison tests?
So we have done the multiple comparison test because the Kruskal-Wallis test showed that the medians are different. They're not the same. But the Kruskal-Wallis test does not have the ability to know which crops, okay, which medians for which crops are different. So Dan's multiple comparison test helps us to identify which pairs, okay, are showing significant differences. That is why we are computing and showing the multiple comparison test. Somebody says they have failed. Huh. Why? Let me see. Okay, so I'm going to crop was coerced, that's fine. Okay, so I'm going to put the question where in the chat. So my question is there a significant difference in the amount of rainfall required for the production of coffee and rice? Coffee and rice. So you look for coffee and rice here. If you have found coffee and rice, paste it there for us to see. And the question is there a significant difference in the median rainfall required for coffee and rice? Okay. So if you also want to see the medians, which one is higher, compute the median. Do a summary, compute the median rainfall for each. And the last question is there a difference between the median rainfall for chicken, pea, and potatoes? Chicken, pea, and potatoes. Is there a difference? Somebody's saying no. Chicken, pea, and potato. Okay, I'm seeing varied answers. Chicken, pea, and potatoes. Is there a difference? Is there a significant difference? Is there a significant difference? Yes. Chicken, pea, and potatoes has, there's a significant difference. There's a significant difference. I think that is correct. There's a significant difference. The person that is failing to install these packages, maybe there is an issue with permission. The person that says they have an error that there is no package, you did not install the package. Now click on the line that has install.packages. Meanwhile, you can let me know if there is a significant difference. Continue to confirm. If the person that says there is no package, please run this line here. Install the package first. Then when you run, then you load the library after. Then you load the library after. Okay? The post hoc, where is mine? Interpretation. Okay, so the post hoc is here. When the p-value is significant, okay, when the p-value is small, less than 0.05, you will conclude that the median for the two groups that are being compared, the median rainfall in this case, is similar, okay? When the p-value is small, that means it is less than 0.05, it is significant. When it is big, greater than 0.05, it is significant. So this value, for example, this one here, is a big value, okay? So there is no difference. This one is small, there's a difference. This one is very big. We are using p-adjusted, the adjusted method. And yeah, so it's more of which one is significant, which one is not significant, which one is significant, which one is significant. Okay. All right. So I'm going to introduce one last topic. So the p-adjusted, unadjusted for the multiple comparisons. The adjusted is adjusted for the fact that you're doing multiple comparisons. Okay, so we can proceed in the interest of time. Now, we also have predictive analytics. Remember, there are 4 types of analytics. We looked at the descriptive, we looked at diagnostic. Now we are looking at the predictive analytics. Predictive analytics involves mainly 2 things. It mainly involves regression and classification. There are different methods that we use when we're doing regression in order to predict outcomes, especially if the outcome is either numerical or categorical. Okay, so if you would like to predict whether a categorical outcome or whether a certain observation will result into a certain category, then you are going to be dealing a lot with classification. But if you want to predict a numerical outcome in data science, then we will be looking at methods like regression, linear regression. There are many different methods that we'll look at. And we will start off with the first method today, which is linear regression. Okay. First of all, regression is a common technique. It helps us to establish relationships between 2 variables. Regression is specified using a mathematical function. So if you're now thinking about regression, then you must be able to understand which variable is predicted and which variable is a predictor. So at this point, when you're doing predictive analytics, you now understand the research question. You have probably identified some relationships from the diagnostic analysis, and you now want to do predictive modeling, okay? So it is important that you don't confuse the outcome or the predicted variable or the response variable that you are interested in, because the relationships that are specified in regression, one variable strictly explains another variable. The variable that is explained, which is the response, which is also the predicted variable, sometimes also referred to as the dependent variable, is the y in the mathematical function. And then the variable that explains the outcome from which you want to get information, okay, to make the prediction, is what we call the x variable. So you need to correctly specify the response variable, okay, which is the predictor, so that you can capture the relationship correctly. The a and the b are constants and coefficients. These are part of the function. that we can estimate using various methods. In this case, we would use the least squares estimation. But it's important that when you want to do a regression, especially a linear regression, you understand which variable depends on the other. And also that the variable that depends on the other is actually a numerical variable. Okay, so this method helps us to do predictions when the outcome is numerical in nature. And you can establish a relationship and then do a prediction and then evaluate the model to see if it is performing well. Now, just because you run a model may not necessarily imply that the model will be performing well. So you have to establish and determine whether the model is performing well. And if, for example, you can now use the model to do the predictions, deploy the model, which is going to be something that we will eventually do before we end our webinar series this week. When you use the model for prediction, can you now deploy that model so that other people can use it? So linear regression will produce a line. It will produce that mathematical equation. It is that equation that helps us to do predictions. In R, we use the LM function, the linear model function, to produce a linear regression, okay? Establishing a relationship between the dependent or the response and the predictor variables of interest, okay? And this regression here can be done as a simple linear or as a multiple linear regression, and we'll see the differences. Now, when we talk of simple linear regressions, these are regressions that have only one predictor variable. Is it possible to predict your outcome using only one variable? Okay, it can be possible. Is the model performing well? That is another thing altogether. So when you have only one predictor variable, that will be a simple regression. In R, as the tool we are using, you can specify the relationship. Just make sure you specify it correctly, okay? So the Y variable should be specified first because it depends on the X variable, which is the predictor variable. Okay, so the predicted variable or the outcome or the response, okay, depends on this. So that is the relationship we want to establish. And of course, we specify the data depending on the name of the data frame. So if we are dealing with a certain data set, then it means that that is the data set that we are going to use. Alternatively, and if you run the regression, we have different metrics that we get, and we shall be explaining these, and then we can also go into detail to evaluate the performance of such models. Specifically, the stars will always represent significant relationships, in which case you will know that the body weight, okay, significantly predicts the milk yield, okay? And that about 89% of the variation in the milk yield can be explained by changes in body weight. Now, you can improve models by adding variables into the model. When you add variables into the model, you produce what we call a multiple linear regression model. And we do this because sometimes the variations in the outcome, okay, cannot be captured by only one variable. So we may need many predictor variables so that we can capture to a large extent the changes or the variations in milk, and therefore be able to improve and predict our outcome more accurately than we would. So it's important that you capture as much information in the predictor variables as possible. So how do you add variables into the model so that you can be able to accurately predict the outcome of interest? So you add variables ideally by using the addition sign. Okay, in the linear regression function, you just use the addition sign and keep adding them. If they become too many, we can put them in one vector and add them at once. But it's important that you know that when you add variables, it simply means that you are running a multiple linear regression model as well. All right, so you can have as many as they exist, okay? Or as many as you have. We shall look at how you can do the variable selection as well, so you don't end up with too many variables that are redundant in your model. But you can add all of them. You can add all of them into the model, and you can run the multiple linear regression model that has very many different variables like the feed intake, the age, the body weight, predicting the milk yield. So again, make sure you correctly specify the predicted variable or the outcome or the response that you are interested in so that you can have a model and you see. So you can quickly see that now we have an adjusted R-squared value of 0.98, okay? Compared to the previous one, which was 0.89. So it means that a combination of these variables, okay, provides a better prediction for the milk yield compared to when you use only one variable, because the R-squared improves. Larger values of R-squared show that the model predicts the outcome better. It captures the variation in the outcome better. So you can use this to make comparisons between models, and also looking at the significance, the p-values here, you can quickly understand which variables are important and significant in explaining the variations or predicting the milk yield. So that's the concept of linear regression. Now, when you do this, it's important that you can actually run the regression so you can see the output and have an interpretation. As I said earlier, we shall also look at how to evaluate these models here. So in new R, we are back in R Studio here. We are going to look at regression. Okay, I didn't send you the code. Open this code here. If you downloaded it already, as we said earlier, it is the linear and logistic regression code. Mine is, I think, still in the downloads. This one here. This is the code. This is the R code that I want you to open. If you haven't downloaded it, that means you have to go to the Google Drive and get it from there. If you have it, open it. Okay. If you have it, open it. Somebody's saying, can you load CSV? Yes, we are going to do that because there are two things that you're going to do. You're going to open the linear logistic regression and also import the data set, the animal data set here, because it's part of the files that you downloaded today, the animal data. So I want you to import it into R. If you have not imported it, come here to import. You can look at my screen. Under your environment, come to import from read R, this one here. we are importing from readr because it's a CSV file, not an Excel file. Then you should be able to browse and find animal data here. Open. And when you see it, click on import. Okay, you should see your animal data here. And maybe I can pause a bit. I can pause a bit so you can produce that animal data. Import it so you can see it here. Okay, 1 for yes, or yes if you've succeeded. 1 for yes if you've succeeded. Okay. Car package is not available. If it prompts you to install, install the package. Okay, so yes, we have the animal data. That's great. We have animal data into our workspace. Okay, so that's perfect. Now, if you have the animal data, as you continue to import it into your workspace, also, if you haven't installed the car package, highlight and install. Should take a short time. Load the library. Okay. After installing, load the library of that package and also the dplyr package. So we are following these. So we start by installing packages that we don't have. And then we read the data which I've already imported, because sometimes people don't have their data in the working directory, so it confuses. So that's why we are importing using the environment. And also, in order for us to use our data in the way that we need to capture it, we are going to transform. We are going to transform our factor variables into factors so that they're captured as factors. So you can just highlight all of them. Okay. And then after, you can keep rows that are do not have missing values, especially for the outcome. Then after, you run the linear regression. So that's the importance of having a script. Run the regression and do a summary of the simple regression model. Exactly how I have done. So you should have the same output. You should have an R squared of 0.89. If you are using the same data and we are running the same models. Okay. Let me see if we are even succeeding. Yes, if you've succeeded. You don't have the packages. Okay. Okay. Let's address some errors here. The first error is this one. The package. Please make sure that you have the package. The preds, I think I removed the preds, so you can comment this one out. Comment this one out. Comment line 16 out. Okay? Because it's supposed to check if and only retain non-missing data, and we don't have non-missing data. So run the regression. Somebody is saying no such file in the directory. Please import the data using the environment if you didn't put your data in your working directory, because it will be easy for you to locate it. If you brought the animal data, if you downloaded it from the Google Drive, come to the environment. Please pay attention here. Come to the environment and from read R, because it is a CSV file, browse and find that animal data from here. Open, and when it loads, click on import. Okay, you should be having it. The reason why you're getting that error is because you are running a regression on a data set which you have not yet imported in the environment. So it's important that you import your data into the environment before you run that. Meanwhile, did you succeed? Comment line 16 out. Comment line 16 out. Comment line 16 out. I would like to know if you have a regression model. Object animal data not found. Okay, there are two errors. When the animal data is not found, it means that you did not import it into the workspace. So please, if you cannot see animal data in the environment here, if you're looking at my screen, you will not be able to perform a regression model or predict any variable in there. So make sure that the data is imported in the environment. And the easiest way to import is to click on import inside the environment, click on import and go to read R, because we are importing a CSV file using the read R function or package. So click on that and browse, then find the data where it is. Otherwise, then you click on import. Otherwise, you cannot run those regression models. Meanwhile, what other challenge are we having? Data imported, but I'm still having the error. Which error? Richard's error says trade not in found. So that line 16, please, can you put a comment on it? Because we don't have this variable. So, and put a comment here, the hash symbol, okay? And run the regression. It's supposed to help you get, information for those that are not missing, okay? And then proceed to the simple linear regression. Okay, so for those of you who have done that, can you also run multiple linear regression? Check if the body weight and temperature, okay, can predict milk yield, and tell me the percentage. It's almost similar. Okay. Now perform the multiple linear regression as well, and let us know the R squared. Okay. The R squared, run the multiple linear regression. This one, the last one, that has many explanatory variables. Run this one. Let us know the R squared that you get. Mine is 0.98, which is almost 98%, 99%. Let me know if that is what you have as well. Let me know if that is what you have as well. Let me know if that is what you have as well. Meanwhile, we use this to do predictions. So the predict function, which is the last function for today, will help us. I mean, somebody's saying, isn't it overfitted? Yeah, it most probably is. But we will be looking at model variable selection as we move forward, so that you can see which variables, first of all, are correlated to each other and which ones you may need to remove from the data, or rather from your model, okay? As we go into machine learning to look at the algorithms and which methods they use. Now, do a prediction of the milk yield using the predict function. Using the predict function. And after that, go to the animal data set, this one here, and see and check to see the predicted values. They are here. It's probably the last variable that has been added to the data set. Now, this is predictive analytics. We are modeling because we want to do a prediction on the outcome. So evaluating the model involves checking and understanding the differences between what has been predicted and what was recorded. So does the predicted value of the milk yield look similar to the recorded value? Because when you carry this model and deploy it somewhere using, for example, another data set, you have to be confident that whatever predictions are coming from the model are similar enough, okay, to what would have been the reality. Because this milk yield, this one in liters, is the reality, is what was captured in the data. The milk yield that is being predicted is what has been modeled by the linear regression model, okay? So it is important to understand the differences between these when you are looking at model evaluation. And also, it helps when you have a good evaluation metrics to see and to know that you are making predictions that are almost similar to reality, okay? So that means that you can, now this particular model here, we have used the entire data set, for example, to do this prediction. But you can also split this data and use part of the data to generate the model, then use another part to, for example, predict and see if the prediction works. We can do all that. But all in all, because we are interested in predictive analytics, we are able to predict the outcome variable basing on the regression model that we have. Now, we can also do a prediction later when we go to logistic regression. You can also predict categories. How likely is it to be in a certain category? How likely is the yield to be high or considered low? So that is what predictive analytics is all about. Let me know if you have predicted. Where did you find the column for predicted? The column for predicted is found when you run the predict function, this one here. So you will not see it until you run the function, because it is the function that does the prediction and stores the predicted values in that variable. So let me know, run this last line of code for the prediction to predict those values. And let me know if you can see it on your end. Let me know, is regression the same as correlation? Regression goes beyond correlation because regression looks at causation. Correlation is not necessarily causation. So if you can see your values that are predicted on your side, then it means you have successfully used the regression model to predict the outcome. That means you can carry these results into another place if you have information about the predictor variables. You can then use those variables to predict the yield outcome. And this helps you in planning purposes, okay? That if you put in this amount of for the predictor variables, for example, if you have fertilizers as part of the predictor variables, if you have pasture quality index, then what pasture quality index do you need in order to achieve a certain yield, okay? So the prediction models help you to have that information so that you can do the prescriptive analytics, okay? And plan basing on the information that you have to make decisions for the future. So seeing that you are able to see your predicted values, I'm going to end here. Please, the person that is putting the error that object PREDS not found, please comment outline number 16. Comment outline number 16 and proceed to run the model. And I would like to end the webinar here and hand over to David. Thank you.
Hello, everyone. It seems like either David is muted or is somewhere. I would like to thank Peace for taking us through today. And I would also like to close this webinar and let's meet again tomorrow. Thank you very much. Bye-bye.